I have the great pleasure to try to present today, together with many other colleagues, the technical part of Africultures, which is very few technical words about how all these products that we're going to see later available on the platform, they have been prepared. So we are, of course, in communication with the local stakeholders through Located, and we have identified through these years what are the priorities for Kenya, which are the products and the services that are of most important to the local needs and requirements of the whole service portfolio that we have been preparing for the whole continent of Africa and for the 8 countries that participate. The services cover climate, crop, drought, land, livestock, water, and weather. And from all these products that have been prepared, we're going to present those that are of special attention to the Kenyan context. We're starting with the crop type mapping, which have been developed by our colleagues from SIA. Giovanni, if you can hear.
Yes,
can you say a few words?
Yes, this is, thank you very much, Thomas. Hello to everybody. So I'm Giovanni Laneve from the University of Rome La Sapienza. And this is one of the products that we have developed within the project. In this particular case, this is a crop type map of the Transzonia district, but actually we have also the similar maps for Nakuru, Narok, other provinces of Kenya. This was actually the map is made by combining 2 maps. One is a land cover provided by the European Space Agency at 10 meters, and the other one is this crop type mapping made by produced by us, and that is superimposed to the land cover. This is made thanks to the field campaign carried out in the field from facilitated in some way from Locate IT and carried out from the University of Nairobi. In order to produce this kind of maps, of course, we need data coming from the ground. Then field campaign are requested to developing the product as well to validate it. So this is Thomas, please. Okay, this is myself. Okay.
Thank you, Giovanni. I'm sorry, due to some technical problem, we wouldn't see the map before, but this is the map that Giovanni was presenting, covering Kenya.
Sorry. Okay, sorry.
Don't worry, it's not your fault. I think we'll solve it. Let's move to the next product about crop condition monitoring, which we use various products that cover NDVI, the well-known vegetation index, leaf area index, which has to do with biomass, and then 2 other products, which is the vegetation condition index and NDVI anomaly, which compare the current situation with the long-term historical data of 5 or 10 years ago, in order to establish if the current crop condition is normal or not, if it deviates from the historical condition in the area. For this, we have been using data from wide-scale covering satellites of 1 kilometer resolution, but very frequent overpass of 10-day composites, also medium resolution at 250 meters, and these 2 can cover the whole continent and, of course, at national level. And also, we have been using Sentinel-2 when we want to focus in very specific areas. This is a result of vegetation condition index and NDVI anomaly on the top. You can see the vegetation condition is not good, especially as we move on to the later June and December. It has to do with rainfall deficit that was reported at the end of the year. On the top image, you can see a lot of cloud cover here on the western side and a bit on the eastern side. This is a main problem that we have with remote sensing data, the cloud cover. And this is usually we use wide area covered satellite images which have capacity to acquire images every day. And by having daily images, we can exclude the pixels that are covered by cloud and replace them with a pixel of the next day. So that's how we can manage to have appropriate coverage without clouds throughout large areas, such as a whole country or even a whole continent. So cloud has been a really big problem with monitoring crops with remote sensing. Going now to very high resolution products, Giovanni again will explain how we do that at high resolution with Sentinel-2 images.
Yeah, this is the same principle already that Thomas described. Actually, we are doing the same than on medium or low resolution on Sentinel-2, then providing a product that we can consider at high resolution. In particular, of course, this kind of product is just devoted to crop areas. So we are not considering areas that are not defined as a crop. This is as already Thomas said, then we have different level of, we define a different condition level from the crop, going from normal vegetation to extreme poor vegetation. And this is based on a comparison between the actual value of a vegetation index, like NDVI, and the average value of the same index in the previous 6 years. So we are considering all the Sentinel-2 images available since 2016. This is also based on 10 year, is provided every 10 years. Still based on the satellite images, then on the historical behavior of the NDVI, not historical, the yearly behavior of the NDVI, we have developed also this crop calendar. Then we provide for crop area, of course, the calendar that is mostly providing the start of season, the end of the start season, the day of the maximum value of the NDVI, or also the maximum value of the NDVI, and on the other side, the end of the season, the start of the end of the season, the end of the season. So, in other words, we are providing a map that is containing 10 bands, then 10 different layers, 10 values for each pixel, in which all these quantities are provided. Thank you, Thomas. Can you proceed? Then, since we have the history of the crop along the year based on the Sentinel-2 images, of course, we can also monitor the phenology of the crop. And then from that, we can also estimate how the crop is, growing the crop this year with respect to the previous year. Then we can identify, for instance, some delay in the growing of the crop or some early growing of the crop, as is shown in the map on the right side. You see the values are going from -4 to 4 because this number should be multiplied by 10. Then -4 means that the crop is in delay of 40 days, or on the other side is growing early with in advance with 40 days advance. So different colors refer to different difference between previous year phenology and actual year phenology behavior of the crop. Okay, Thomas? Concerning another product is this crop early warning. This is done at medium and high resolution. Also, this is based on combining information coming from different sources, in particular meteorological information, then precipitation status, thermal anomalies, and of also the vegetation conditions based on the NDVI. Here we have, for instance, 2 maps of Kenya at 2 different times. According with the color, we have a certain area in which we have, for instance, a low level of warning, because we define 4 levels of warnings. The first level is occurring when just the vegetation is showing an anomaly. than the NDVI, then the level becomes 2, 3, or 4, according that the anomaly is also related to precipitation anomaly, then less precipitation than the previous years, or thermal anomaly, the higher temperature than the previous years. So this is done at medium resolution and also at higher resolution. You can go on the next. Then this is just to then we combine the NDVI, the map of the vegetation, with the meteorological condition, precipitation, and temperature, and then we come out with this product that is called CLUE, where is a crop early warning product. So this is just an acronym of the product. Then we are using VCA. Okay. So this is the same is done at high resolution. I'm just reporting in this case. Then the estimation of the crop conditions is based, as said already before, on the comparison of the actual values of the NDVI with the values in the same 10 days or weeks of the previous 6 years. Then it's a comparison with the previous years. Okay, Thomas?
Thank you very much, Professor.
Okay,
and we move now to crop yield forecast. We have been doing that in low and in high resolution. For high resolution, we need a lot of data collected in situ, which has to be given in time. And then we compare that with very high resolution images and machine learning, and we get results at a very local scale. This we have done, unfortunately, only for rice in Mozambique. I'm going to show you now the results from our colleagues from the University of Leeds, where they have been using global crop yield models in order to estimate the yield of 8 crops in Africa. Here are the results for 3 crops in Kenya, and you can see on the right what is the predicted and what is the actual yield for many years that we have that they have run this model. Unfortunately, let's say the results are not as good as we wanted for potato, and neither for maize, but for wheat, the forecast show a very good skill, and they should be they could be used for forecasting the yield of the next years. Now let's go to water. First of the products is the water bodies mapping, and we refer to surface water bodies. For this one, we use the global, the Copernicus water products, and again in 2 resolution. One is in high and medium resolution at 100 and 300 meters, and then medium and coarse resolution at 301 kilometer. The main advantage of having the high resolution products is that we can, the coarse resolution, you can do it very frequently, every 10 days. Here are some results on top for Kenya, the whole country. In various colors, you can see where water is and how frequently water occurs there throughout the year. For example, dark blue and blue is very high occurrence, which is the permanent water bodies. On the lower image, you can see in Nyanza the water extent of Lake Victoria, and in Central you can see smaller water bodies as they have been appearing throughout the year. Now let's move to water consumption. These indicators are very important for water management. They refer to large areas and to large time frames. So they can be used to identify how much agriculture is using or water, and how much potential is in an area to develop further the water resources that are available. They are not of very high resolution and not very frequent, and not provided timely enough to be used for irrigation scheduling, for example. But the products we're using again cover wide area, and cover the whole of Africa at 3 kilometers or 5 kilometers resolution, and then higher resolution of 200 meters or 100 meters in order to cover areas that are of particular interest. These products are quite difficult to produce. They're based on the surface energy balance equation, and they require also thermal bands. That's why the spatial resolution is not as high as the other products. Here are some results of the actual evapotranspiration and interception at 10 days, every 10 days in a millimeter per day. This is the average of the 10-day period. And it is the sum of the soil evaporation, the canopy transpiration, and evaporation from the rainfall as it was intercepted by the leaves. You can see in various colors. On top, the nationwide product at 250-meter resolution, and at the bottom, some various areas at 100-meter resolution. Stay in water and go now to lake water quality, where Professor Laneve will describe this product.
Yes, sorry, I was muted. Yeah, this is another one of the product available on the platform of the project. I have to underline that, of course, some of the product, we are not developing everything from all the products from the beginning, but some of them are taken from other initiatives already available. Then this was, of course, a way to save time. In this particular case, also this information is coming from Copernicus, from the European initiative. And what we are providing here is the two parameters characterizing the status of the water of the internal water bodies, the lakes. These are the turbidity and the trophic state index, that is an indicator of the productivity of the lake. So you see an example of the Turkana Lake in particular, in which you see the scale giving us an idea of the trophic state of the lake, then the pollution in some way of the lake. Also, this product is provided with the scale of 10 days, temporal scale, spatial resolution of the 300 meters. Okay, Thomas? Concerning still water, another product that is available is the soil moisture on our platform is the soil moisture monitoring. This is a low resolution product. Actually, the resolution is of 10 kilometers. The product is provided every 10 days. This is in this slide, what I like to show is that the product that we are delivering are most of them validated. This is in fact the particular case of Kenya, in which the product provided by the satellite were validated using information coming from ground stations. So you can see in the bottom right plot the comparison between the measurement done of the soil moisture done from the ground station and the one provided by the satellite. As you can see, if you compare the dotted line is representing what we are providing, the points are what is given by the ground station, then you see that there is a very good comparison between the different dates. Then this is, I think, important to know that at least on some of the products you can trust in terms of accuracy, I mean, validity. Okay, thank you, Thomas. This is together with the previous product, we are also developing, this is done by us, it's not on the website of Copernicus, is this soil water condition index. So comparing the soil water condition of the particular day of the year with the previous 10 years. So we have an idea of how the soil moisture is, how is the behavior of the soil moisture or the trend of the soil moisture this year with respect to the previous 10 years. So this could be a good information for judging the behavior of the weather condition of the water availability of the present year. Thank you, Thomas.
Thank you very much, Professor Laneve. Let's move now to livestock and see the products that have been developed by our partners, the South African Space Agency. If Mr. Maklapse Kanyago is online, can present them.
Yes, hello everyone. My name is Matlhatse from South African National Space Agency. and I'll be presenting on the livestock services. So we're developing decadal rangeland type maps, which provide the distribution of the rangelands over time so that we can be able to monitor their changes. And for this, we're using MODIS land cover, which is more annual. I can't see the slides anymore. It's an annual product.
You're right. Hold on, Mahlatse. We'll
okay. Yes, thanks very much. So it's a annual product. So it provides us with a much needed frequency. So we create some training and validation data based on the MODIS land cover, and we assess the accuracy of the samples and map using Sentinel-2 and Landsat. So the data is at high resolution. And for the coarse resolution, we are using the JRC data, which also characterizes the distribution of rangelands, but at 1 kilometer. I lost the slides again.
Hold on, we still have some problems, Mahlatse.
Okay, but can you see the slides from your side?
Not yet.
Oh, okay. So yes, so this is the graph that shows the sample assessment. So we select the best samples out of the MODIS product and use that for mapping using machine learning algorithms. As you can see, we have two maps which characterizes the grazing and browsing areas for 2010 and 2020. Next slide, please. So we also provide rangeland condition maps, which provide seasonal pasture conditions. And for this, we're providing a number of indicators such as the NDVI at high resolution, leaf area index, the chlorophyll content, which is a proxy for nitrogen or nutrient content, and also a fractional cover. Thanks very much.
Thank you, Mahlatse. I think we can wait for 1 minute until this problem is solved, because the next speaker again will be online. This is the rangeland condition map that Mahlatse was describing. And we can now move on to drought monitoring and early warning. And my colleague, Vasilios Pavlidis, Dr. Vasilios from the Aristotle University of Thessaloniki, will present.
Thank you very much, Professor Alexandridis. Can you hear me?
Yes, but we cannot see the presentation. I think we have to find a way to show the presentation.
Okay.
Actually, I can see.
Actually, I can see it as well.
Okay, but the audience here.
Okay.
So.
May I suggest that Giovanni or Vasilis present the same presentation, share their screen? Maybe that would solve the issue.
Let's try. Share.
Okay, I think we can see the screen of Giovanni full of icons.
You can see.
Okay, good.
But I don't know why I cannot see.
Okay,
but if you can see, it's okay. So can you, yeah.
Can you put the presentation on?
Let me, yes.
Okay,
this is.
Yes.
You can see now? Okay.
Yes, make it in presentation mode, please.
Yes. Okay.
Thank you. Let's see now if Vasilis can speak while we see the screen of Giovanni.
Great. So my name is Vasilis Pavlidis from the Aristotle University of Thessaloniki, and I will present the drought monitoring and early warning service. In this service, we try to identify the current status of drought, and also provide some early warning messages. We use a variety of indicators that try to capture the different impacts of drought on the physical system. For the precipitation deficit, we use the standardized precipitation evapotranspiration index, both the 3-month and 1-month SPI, to capture different scales of accumulated drought. For the soil moisture, we use the soil water condition index that was presented to you before. And for the vegetation status, the drought impact on vegetation status, we use the vegetation condition index that has also been presented to you before. The SPI is based on the analysis data, and the soil water condition index, and VCI is based on satellite data. And moreover, we also try to combine all these indices using the methodology issued by the European Drought Observatory to construct a combined drought index in Africa that tries to capture the status of drought with simple to understand messages and specific color coding. We use a similar but different set of sub-indicators with respect to the European Drought Observatory. And we can see in the screen the different signals of the CIA and the physical procedures that these are connected to. For example, for precipitation deficit, we get a yellow color coding, and for soil water deficit, we get an orange one, and the most severe signal is the vegetation stress, the alert, the red one. The CDIA is given on a spatial resolution of 10 kilometers and on a temporal resolution of 10 days, every decade, every 10 days. Next slide, please. In this picture, we can see the maps of the drought monitoring service. At the bottom middle, we can see the combined index for the first 10 days of March with the gray background, and all the different sub-indicators used to produce this combined index. And we can see that we use the SPI of the previous month and the vegetation condition index and soil water condition index of the previous 10 days, which are the most recently available data. And next slide, please. And to finish this presentation, besides all these indices and the combined drought index, we also provide some complementary products. For example, the precipitation anomaly based on the IMERG satellite products, and the anomaly is calculated with respect to the climatology based on the RFID analysis data, and also some interesting forecasting products, such as that might be of interest in drought. For example, the precipitation deficit that shows locations with no precipitation occurrence for the next 7 days, and also the probability of extreme high temperatures, both based on the NCEP GFS forecasting system. That's all for the drought monitoring service. I think Sixo is with us to present the seasonal drought forecast, otherwise I can do it.
Yes, can you hear me?
Yes, yes.
Yes.
Okay, perfect. Well, the seasonal drought forecast try to complement the drought forecast presented by Vasilios with the same or more or less the same indicators, drought indicators, but for the next season and the next 6 months, and the probability of normal condition or drought condition or weather condition than normal for the aggregated value for the next season. Then this is based on the multi-system seasonal forecast of Copernicus. So the spatial resolution is 1 degree and the temporal resolution is multi, and we have different products to describe the evolution of the drought index for the next 6 months in the case of the ensemble mean of the multi anomalies, and the probability of the drought condition for the next season in the terms of the next 3 months aggregated to have only one value and compared with the terciles obtained for the reference period, which is the 1993 and 2016. We make the verification based on the ERA5 error analysis produced by the European Center, and considering these hindcat periods for all the season at all the countries. We make the evaluation at country level and continental level, and using different statistics. On the one side, we have the deterministic evaluation, which is based on the ensemble mean, and the probabilistic evaluation, which is based on this third side that we are choosing, based on the different parameters that are reflected in the slide and are properly described in the deliverables of the product. This forecast is available every month, and it's produced every month, and is complemented also by with the climate parameters in the terms of precipitation, temperatures, and runoff, and with the same product for these climate variables. Can you go for the next slide, please? Thank you. This is the map for March, the seasonal drought forecast for March for the different products. We have on the left side the potential evapotranspiration for both the raw value and the anomaly with respect to the hindcat period. As Vassilios said previously, we came from drought condition or dry condition than normal, and as is reflected by the both SPIs with 1 lag month and 3 lag months, it seems that we are going to weather condition for the next months. At least this is what is reflected by the figure. And if you go to the next slide, and it is also reflected when we see the probability of the higher tercile in the sense of weather condition than normal for the SPI3, which is the index that has the best skill for this area. On the right of the slide, you can see the temporal correlation for this season, March, April, and May. And as you see, the correlation for the SPI3 with 3 months of lag is quite good around the most of the continent. And the column that you are seeing is the relativity diagram, which reflects in color the usability of the seasonal forecast for each of the terciles. So in principle, the accuracy or the reliability of the seasonal forecast for the SPI3 is quite good in Kenya, with the exception precisely of this next season, which is March, April, or May, but in general has a good result for this country. So I think that's all.
Thank you very much.
Thank you.
That was Professor Sixto Herrera from the University of Cantabria in Spain. And,
sorry, I don't present myself. Sorry.
It's my mistake. I didn't present you at the beginning. Sorry. But thank you for joining, although you have a very busy schedule today with your lectures. And now I would like to ask Dr. Grigory Nikulin from the Swedish Hydrological and Meteorological Institute to present the projections, the climate projections for the next decades.
Good morning, everyone. Can you hear me?
Yes.
Good. Yes, my name is Grigory Nikulin, and I'm from the Swedish Meteorological and Hydrological Institute. And I'm presenting 2 services, what we did in Africultures. And the first one is decadal climate prediction service. So here we provide operational decadal prediction. And decadal prediction is basically simply a forecast up to next 10 years. So here we present 1 year forecast for 2021 and 1 to 5 year forecast. So it's an average over 5 years from 21 to 2025. And here we present 2-meter temperature and rainfall anomalies with respect to 81-2010 period. So generally, we just saying, is it supposed to be warmer or colder, drier or wetter, and with a 1 year lead forecast and 5 years. And this decadal climate prediction service is based on an ensemble of 8 global prediction systems that we're receiving from World Meteorological Organization. And also we're providing information about the skill of the forecast, because of course we need to know, is it skillful or not? And here as an example, it's decadal climate predictions for these two forecasts for 1 year, 21, and for 5 years, 2025, for rainfall. So basically where we see dots, it means that this region has no skill in the prediction. But still we can see that some regions have some skill, especially if we take 5-year average for 2021-2025. So these products are available through the Africultures platform, and a new operational ensemble is generated once every year. So we're going to make an update for 2022 and 22-26 by the end of May, when a new data is available from one of the WMO centers. Please, next slide. And another service, it's climate projections. So here we provide data from a regional ensemble at about 50-kilometer resolution from coordinated regional downscaling experiment for Africa, or shortly Cordex Africa. And here we provide 11 variables and indices. So 6 of them are related to temperature, 4 to rainfall, and 1 to wind. So we take exactly the same variables and indices as in Intergovernmental Panel on Climate Change 6 assessment report atlas. So basically here we very well synchronized. And in our service, the information about 3 scenarios. So it's RCP26 for 5 and 8.5. And also we're using 3 reference periods, one defined by WMO recently, it was from 81 to 2010, and 2 periods that were taken from 5th and 6th assessment reports of IPCC. It's 86 2005 and the recent one 95 to 2014. And then we provide information for projected climate changes over Africa for 3 future periods. So it's 2140, 4160, and 2100. And they refer to near, mid, and far-term future. And also we provide information for projected climate changes over Africa for 3 different global warming levels. So it's 1.5, 2, and 3 degrees. So users can select any season and combine it from different months, or just to select individual months. And also we provide information about significance and robustness of the climate change signal, because of course we should know how confident we are if we provide information about climate change, and this information is available for spatial maps. And all these maps can be downloaded as a PNG, NetCDF, or GeoTIFF format. It's also possible to get time series averaged over any country on the African continent or any polygon. And then it can be downloaded as a simply ASCII comma-separated values files. So people can run additional analysis already locally, just getting these files where all ensemble members are available. And again, it can be selected any season or any individual months. And due to complexity of this climate projection service, it has been decided to host it at a different platform, not directly at the Africultures platform. So now it's located in this address below. Yeah, so we're still missing manual. So of course, everyone is very welcome to have a look. And I think user interface is very clear and intuitive. But still we're working under manual that should appear maybe in coming few weeks. Oh, please, next. And here just one example, it's just a screenshot of this platform for providing climate projections. So here on the left side, you can see how you can select different climate variables. For example, related to precipitation, it can be consecutive dry days or maximum 1-day precipitation and standard precipitation index. And also you can select different periods, different seasons, maps. And below on the left side, you can switch on selection of a country or any shape, what you want, and then you can download all this data. So you are very welcome to have a look and to try to work with this portal, and of course to provide feedback to us. Okay, thank you.
Thank you very much, Grigory.